So let's talk about garbage collection. So just about me for 1 minute. So what I do, I try to improve the web. I'm an MDN contributor. MDN is the JavaScript, the open web documentation that the Mozilla people have. And by the way, there is a documentation sprint coming up on this Saturday at the Mozilla San Francisco office, so come by. I try to contribute to open web standards, ES Discuss, mostly, for those who know. So that's the main list where people talk about the future of ECMAScript, what Brenda and I talked about this morning. You can find me on Twitter, send me emails if you have questions, comments. I'd like to say a quick word about this guy. Who knows who Matthias Binas is? That's it? Just one person? No one knows? Oh, okay. Sylvain runs did a conference, a JavaScript conference recently, several months ago, and he was a speaker there, and I ended up eating Chinese food with him and other people, and at some point he asked me, so why don't you go talk at conferences? And I was like, I don't know what to talk about. Then he was like, you wrote this article about garbage collection on MDN, so I don't know, maybe you could talk about that at a conference. And so I guess here I am. So thank you, Matthias, for encouraging me. And if you have something you want to talk about, submit talks to conferences. Don't hesitate. You're not too dumb, or you have things to talk about too. Okay. Before talking about garbage collection, let's talk about memory. So who here has done some C and C++? Okay, that's a good amount. For those who have not, you can think of memory as a very long array where each slot has a fixed size. It's pretty much what Brett and I explained this morning about what Emscripten does. It allocates a huge typed array and use that to emulate the C memory. And everything you use in JavaScript, like strings, numbers, object, booleans, etc., is going to be allocated in this huge array. Okay, garbage collection. Why do we care? Well, the reason we care about garbage collection and releasing our memory is because of these kind of things. That's memory. That's the hardware that holds the memory of your program. You have one in your laptop and in your desktop and in your phones and etc. And that's limited. Yeah. The second question that would come is, why do we care now? Culturally and historically, people have been so in JavaScript runs in the browser, and people have been and even if you had a memory leak in your web page, people would not notice because they would have change of time after 5 minutes or 10 minutes, and any consequence of the memory leak would not be noticed. But that is changing. There is now the trend of single-page applications, JavaScript-intensive applications like games. There is Node.js, and we expect things to run like for several hours, for a day, maybe for a month or a year for Node.js servers. So we start discovering that there is memory, it's limited, and we have to take care of it. Okay, so let's talk about the memory life cycle. It's pretty simple. You allocate something. So the JavaScript interpreter does that for you. Then you use the memory. That is, you write on it and you read it. And then you have to release the memory when you don't need it anymore. So in C or C++, you have to do that manually. In JavaScript, the garbage collector does the release for you. But the good question is, when do you not need memory anymore? And this talk is about that particular part of thinking about this idea of not needing memory anymore. So so you're writing your code, and the good question you have to ask yourself for every single object or string or etc. is, when do I not need an object anymore? And that's actually, when you think about it, it's actually a hard problem, especially when you have several layers of abstractions and different libraries, etc. It's also a problem that's undecidable for machines, and if it weren't, we'd have perfect garbage collector, and we would not be talking about it. But we have garbage collectors anyways, even if the problem is undecidable. So a garbage collector is a program that runs with the JavaScript interpreter, and that's true for JavaScript and all other languages that have a garbage collector. So that runs in the background and it tries to find objects that are not needed anymore. And when it finds such objects, it releases the associated memory. So as I said earlier, it'll fail to do it perfectly. But practice shows that it works. That even if 100% of the work cannot be done automatically, the proportion that can is so big that it's worthwhile to have garbage collectors. So now I'll be describing two algorithms that I know, and I don't know if there are that many more. Two garbage collector algorithms. And I would define a garbage collector algorithm by its definition of what not needed anymore means. So just for a visual vocabulary, I'll be talking about objects, which I'll represent as a dot or circle, and references between objects. So you have two objects, and you have a reference, which is an arrow. And objects and references naturally form a graph of objects connected to one another. So in JavaScript, how do you make a reference? Well, one way to make a reference, for instance, is if you have two objects, and one has a property that links which value is the other object's. Here you have a reference. Another form of reference is, so here you have the f function, and this function has a scope, and this scope links to as an implicit link to the scope of the IFI, which contains the O objects. And so you have different objects that link to one another. And as you can see here, the objects that the runtime manipulates are not necessarily created by you directly. So the scope object is sort of implicit. So the first algorithm, oh, that was supposed to be red. Okay. So the first algorithm, the most naive one, is called reference counting. The idea is very simple. Each object has a counter that counts the number of references to it. So here you can see the object with two references, which has a counter of 2, and objects with counter of 1, and an object with a counter of 0. And this algorithm, the reference counting garbage collector algorithm, decides that an object that does not have any reference to it anymore is garbage and can be then collected. And that's a pretty intuitive definition. And so the idea is that whenever an object has one more reference, the counter increases and decreases when a reference is lost. The problem here with this algorithm is cycles. If you have two objects that reference to one another, maybe these two objects are not needed anymore. But the algorithm is too naive to notice that because it only looks at the counters. So that's a problem. That's too naive. Second algorithm. So this one is called mark and sweep. So the idea is that some objects are special and are called roots. And every once in a while, the garbage collector will stop your JavaScript, traverse the graph starting at the roots, and every single object that is not in this graph is going to be considered as garbage. And this algorithm is the one that is used in all modern browsers, as far as I know. And every single work, every work done in garbage collection research, as far as I know, in browsers, is optimization of this algorithm, but not new algorithms. So as you can see here, you have some objects that are considered roots, and you have a graph of references. And there is this one object that's isolated, and this one is considered garbage. As you can see here, if instead of one object you had this cycle, that wouldn't be a problem because the cycle is not reachable from the roots. So the cycle is not a problem if you have the mark and sweep algorithm. That's a common thing you hear, that cycles are a problem. Well, cycles are not a problem if they are isolated from the roots. So yeah, something to keep in mind. So, but this algorithm isn't perfect either. The first complaint is that it's stopped the world. So the idea is that your JavaScript stops when the garbage collector runs, and the garbage collector tries to traverse every single object that it can find from the roots. And if there are thousands, millions of objects, it can take time. It can take, I don't know, 2 seconds, 3 seconds, and that's a pause during which no JavaScript runs, meaning your user cannot interact with your page, etc. So, but that's sort of a problem. I'll tell why later. Another problem is that, as I said, garbage collector is not a perfect process. So there are cases where some objects are garbage, but this algorithm doesn't find it out. But it's actually much harder to build a use case in which that happens. It's more connected to your code and to the very logic of your code. Oh yeah, I forgot to. So everything I explained here was actually not directly related to JavaScript. It's all objects and references, and so all these two algorithms work in any language. Yeah. So the mark and sweep. So the stop the world problem is actually not that big of a problem because there are optimizations. One of them is called incremental marking, and the idea is that the garbage collector is going to stop your program, but only for instance, 50 milliseconds at most, and then stop the marking, stop traversing the graph, let your JavaScript run, but keep some guards to make sure that the garbage collector is aware whenever the shape of the graph changes, so that when it starts again, it knows where to traverse again. Yeah, there are other optimizations like concurrent marking, parallel marking. There is one cool optimization called generational garbage collection. So some researchers looked at how the garbage collection works, and they noticed that that was in Java and Python programs, I think. There were most of the time 80 or 90% of the objects that were dying between 2 cycles of garbage collection. And so they thought about this refinement where you would not allocate objects anywhere in the heap. You would allocate all the objects in a first generation called the nursery. And anytime it runs the garbage collection, it only runs it. So yeah, when you found the survivors in the nursery, you put them in a new generation. And so you don't need to go to every single object to release them, which is already good by itself. But more than that, a full marking is not performed every time. You only start at the nursery, and you do the rest of the garbage collection less often. So references. So the trick to avoid leaks is just to avoid references to objects that you do not need anymore. So if you end up in cases where you have not naturally broken all the references to an object, well, you have to do it manually. So for instance, here you have 2 objects, O2 references to O through its A property. So here what you just do is use the delete operator, where you remove the A property of the O2 object. Yep. A word on delete. You can read on the web sometimes that delete releases memory. That just don't listen to that. Delete is just the opposite of object.define property. Object.define property defines a known property on an object, and the delete property just removes the property. So that's a way to break a reference, which may end up in garbage collection of the object that was connected, but not always if there are other references to this same object. So yeah, so keep that in mind. And another example to break the reference I was talking about earlier. So if you have, if the reference is related to the scope of a function, what you can do here is have an explicit function that you will have to call explicitly that makes that the a variable does not reference to this particular object anymore. So yeah, so that's one more way to break a reference. There are obviously other references I didn't talk about and other ways to break them sometimes. I think that's it. If you have any question. Yeah. So here I cannot do delete A. It doesn't make sense. It won't do anything. Actually, it won't crash the program, but it won't do anything. Yeah, delete A will just, I think it will return false. And in strict mode, it will throw an exception. So yes. But one thing so the goal here is just so that A, the variable A, does not refer to the object anymore. So you can put any value actually. It can be a new object, it can be null, it can be null, it can be a number. But the point is just assigning a new value. So yeah, the idea is to break references. So at what point the memory will be released, that's up to the garbage collector, which runs in ways you do not control. There are some tricks sometimes in some browsers, but in theory, the idea is that you should not be relying on anything. The job of the browser is to make the garbage collector as discrete as possible and as efficient as possible. And that's your job, just to not keep references when you do not need objects anymore. Yep.
Are there any tools for visualizing, I suppose, the relationships between objects? Like if you're trying to hunt down somebody?
So are there tools to visualize the reference graph? And the answer is, as far as I know, no. And it's pretty sad. I'm planning maybe one day to build such a tool as a Firefox add-on, because they have this JavaScript API, this JavaScript debugging API, where you can stop a program and basically reflect on the entire JavaScript runtime. So you could look for every single object and find all the references and see who points to who and draw that, and even change that at runtime given the breakpoints. But yeah, as far as I know, there is no tool that does that. Yeah. Any other questions? No? Okay. Thank you.